So let's start from the very, very, very beginning. And so go ahead and draw a circle. We'll name the center T. And remember the templates are on the side of the bookcase if you would rather use a template at any time too. Let's draw a simple angle. We'll label the intersection C up here and A down there. This is our first type of angle that we did last week. What's his name? When the vertex is on the center, he's called a central angle. So the vertex is on the center. Do you remember what the sides are without looking? Yep, sides are radii. Oops. Your angle has two sides that are both radii. We had one theorem about him, that the measure of the central angle, he's 112 degrees. Then the measure of the arc that it opens up to, or the pizza crust that it opens up to, is also 112 degrees. So the theorem says the central angle is congruent to the arc that it opens up to. Easy enough? Okay, so all we do in the next few sections is move the vertex around. So the vertex is here on the center. So we really start today. So go ahead and draw another circle. We'll make the vertex T again. The intersection CA again. But where is the vertex? This is our first case. This will be our second case. Where's our vertex? You got it. So the vertex is on the circle. So I have moved it. His name changes. He is now inscribed angle, inscribed angle, when the vertex is on the circle. Who are his sides? They're not necessarily radii in this case. What would they be? Chords. Excellent. The sides are chords. He has one theorem about him, and the theorem says the angle is half the arc that he opens up to. The angle measure is half the arc it opens up to. I don't think inscribed are bad. You just have to remember the difference between inscribed and central. But there's one picture that we need to draw, so go ahead and do another circle. Here is also an inscribed angle because the vertex is on the circle. So you forget that he opens up to not as easy of an arc to see because it gets sort of tucked under there in the circle part. And so some of them, so for example, if the outside arc was 300, what would be this remaining arc, everybody? 60. And then if I asked you to find this angle measure, he's half of it, so the angle would be 30. Absolutely. So not only do these two chords stay in the circle, in this case, the inscribed angle has one side that is a chord and one side, what would you think that would be? If you would touch it and bounce off, tangent, You got it. So there can be some different combinations of the sides, and the sides do not matter, it's where the vertex of the angle is. And if it's on the circle, then you have to pay attention to find the arc that he's open up to. Okay, one more picture. Same concept, different inscribed. Again, I'm going to go ahead and purposely draw a diameter in for this example. This is a theorem in your book, but I think it's kind of one of a duh theorem that I don't know if anybody would need it. So at least we'll draw a picture of it. Some books make it a theorem, some books don't. So if I was to look at this, this chord, this is good enough to be called the diameter. Do you agree? Going across here. And it divides the 360 degrees into two, 180 and another 180, right? Okay, so we know from C to B, and actually we probably could use another letter because it is exactly a semicircle. But these marks show that we have half of a circle, so we have 180 degrees. Do you agree? Now, sometimes you can't see an inscribed angle, or sometimes you just need a little bit of help. But here is the inscribed angle because the vertex is on the circle. And if I take and extend both sides of my angle and make them nice long rays, we can see that the inscribed angle would open up to the whole semicircle. And if the whole semicircle is 180, then the inscribed angle is going to be not 180, but 90. Yep, would be a right angle. Would be a right angle. So this book does not, but the old book makes a point to say that if you have an inscribed angle opening up to a semicircle, then it has to be a right angle. But if you knew the inscribed theorem already, that it's half of the arc that it opens up to be, then you'd already know that he is. Good? Okay, we put our last case scenario, we put two inscribed angles, weirdly enough, together. And we actually put a quadrilateral sitting in this circle. What do you call it when a quadrilateral has been drawn inside? Do you remember that word? It begins with in. We call it inscribed when you draw it in. Do you remember we circumscribed in chapter 5 and then we inscribed? We drew it in and we drew it out. I'm gonna ask for x here. I'm gonna ask for y here. I'm gonna say 114. Yep, 114. And we have 52 and 80. And we're gonna add a theorem to this. Okay, a quadrilateral inscribed in a circle. Do you remember what a quadrilateral's only characteristics are? 4 sides, 4 angles. All 4 angles add to 360. That's the only thing we know. Then we broke quadrilaterals down in that chapter to parallelograms, trapezoids, and kites. In the parallelogram family, do you remember that opposite angles are congruent? And do you remember that consecutive angles are supplementary due to the parallel lines? Well, in my quad, it doesn't look like I have very many parallel lines. Do you agree? So this theorem goes a little bit different. Anytime you have a quadrilateral inscribed in a circle, the theorem says opposite angles are supplementary, which means they add to 180 degrees. And this is the one that, if you ask me in July, like sitting next to the pool, I really have to think about, because it's been ingrained so many times that a parallelogram opposite angles are congruent and consecutive are sup, that I have to think about this one. So when you have any quadrilaterals inscribed in a circle, opposite angles are not going to be congruent. What are they going to be? Sup, which means they add to 180. So do you agree with me that I can find y really easy because you have 114 and y are opposite? So take 180 minus 114 and what do we get? You got it. So 66 degrees would be the answer for y. And you would hope that you'd have enough characteristics to do supplementary here or something, but you don't. You have nothing. Only opposite angles are sup. So you sit there and you go, okay, angle x. If this does not partake in the picture, then I have to think what kind of angle is he. And he is inscribed or central where his vertex is? Inscribed. So Abby, what do you think?
Take 80 plus 52.
You got it. Excellent. So you're going to take the sides of your inscribed angle, and if you can't see it, just really make them longer. And by taking the sides of the angle that I'm looking for and making it longer, we see that it opens up to a huge arc. And the arc is not just 52 and not just 80, it is 132 degrees, this whole arc. And so now if I'm inscribed, then I can find angle x. How? Because you would just take that number, 132, and divide by 2, and what do you get? Yeah, totally fine. Could you find this one then if I asked you to go even further than the book does? And then these would be what? Congruent or supplementary? Okay. Is that good on that one? Do you see how they're more puzzles? And in fact, when we do a worksheet tomorrow, I'll give you Post-it notes, because sometimes I think, like, if I take these 2 pink sheets, if I pretend that they're Post-it notes and I try and find where my angles end, then I can really see the arc that it opens up to, and it's really kind of easier. Okay, so where is our vertex? We've moved it from the center to where did it go now? On, right? And we're still going to keep moving. Are you ready? Okay, next circle. So draw another circle. so this is case 3. This is case 3. And I have a name for this, but maybe you'll come up with a different name that you like better. Angle 1 or X is right there. Where is the vertex? And I'm going to put center T still back. Where is my vertex? It is not on the center. It is not where? On the circle. So where would my vertex be? I call it floating inside. Does that sound good? Okay, so vertex. Floating inside, not on the center. Let's put some letters. A, B, C, D, and I'm going to put E down there. Just in case. To find the measure of angle 1, you sort of think about the arc that he opens up to. So here's angle 1. His vertex is floating inside somewhere, not on the center. And so he opens up to arc AC. So I'm going to do that one. So you're going to take arc AC. Then his vertical partner would be underneath him. Do you agree? Do you agree that angle 1 and underneath would be congruent because they're vertical? The vertical partner's arc would be all of this. Do you agree there? And so that would be arc BED. You add them and divide by 2, so it's the average. So in order to find an angle's measurement who's floating somewhere in there, you take his arc plus his vertical partner's arc, you add them and divide by 2. Let's do an example. So draw another one. So to find the measure of angle who's not on, vertex is not in the center, you find his arc, which is 35. You find his vertical partner's arc, which is 15. And you always do PEMDAS, you always add first in the numerator and then divide by 2. So 35 and 15 is a whopping, divide by 2 would give me a nice 25 degrees. So how do you, I see this on the SAT and the ACT just a little bit. All they do is move this angle 1. So they put it here. And they don't give you this arc. They don't give you this arc. They still give you the 35 and the 15. So you have 2 thoughts on how to solve it this way. You could still find this angle like we did, which was 25 degrees, agree? And then what would it be to angle 1 from chapter 1? Or what is 25 and angle 1? They're supplementary because they're a linear pair, right? And so 180 minus 25 is 1. 180 minus 20 is 60. 160 minus 5 is 155. Agree? The other school of thought you could do to solve for this angle that's missing, that's not directly easy, is that if you think about it, if I go all the way around the circle, how many degrees is it? 360. So if I take this arc and this arc, I don't know what each of them is, but I know what they would add up to be. And isn't that the numerator anyway? Because the whole circle is 360. And I've taken up 50 of it, so I have 310 left. Agree? Now, I don't care if this is 300 and that is 10. I don't care the split, because what do you do in the formula anyway? You add them. So no matter what this arc is and this arc is, it would be 310 divided by 2, and we still get that same answer. So two different ways to do it. How's the angle inside but not on the circle? Okay, where are we moving next? We've done in the center, on, now floating in, now outside. Category number 4. Category number 4, vertex moves outside the circle. Many textbooks break it down into how they look, and I'll show you, but I don't think you need to break it down. I think we just need to know one formula. I'll break it down for the first one, and then I'll show you why it looks pretty easy then. Angle 1, or x, or whatever, is outside. The vertex is way outside the circle. Put some letters A, B, C, and D. Okay, since the vertex is outside, do you see that its sides are intersecting the circle 2 times? So the top one would be called A, and the bottom would be called A. So they go through each situation, and I'll show you each, but I think one general formula is going to be enough. So they would call this one secant secant, but the vertex still is outside the circle. And if you noticed that when you have the angle, it intercepts or it opens up into 2 arcs. You have a smaller one and a larger one. And so my formula, just general, take the larger arc minus the smaller arc and divide by 2 to find the measure of that angle 1. Big arc minus small arc divided by 2. Let's do it again. Let's change the way it looks and show you the formula stays the same. Okay, what do you think this one would be called? Vertex still outside. Angle 1 still has the vertex way outside. This is not secant secant, this is secant tangent. Excellent. Secant tangent. And if you notice, we still have a big arc and we still have a small arc, so the formula is still true. Now we have one more, but you're already smarter than it. So what would be the next one? If we did secant, 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 tangent, what do you think the next picture is going to be? But tangent, tangent we already did, and I gave it a funny name. What did I give it? The party hat. So we sort of already did it. I'm going to make this shorter. So we'll call this one tangent, tangent. I'll put angle 1 way out there at the top of his hat. And we had the tangent, tangent with the side congruent to the side, that the two sides of the party hat have to be absolutely perfect. But now we're still dealing with the angle. We don't want the sides. So we have the exact same thing, everybody. We have big arc minus small arc divided by 2. Big arc minus small arc divided by 2. So it does not matter what you have. The most important thing is that where your vertex point is, then we have the same formula over and over. Big arc minus small arc. Okay, we're finished with all the angle formulas. How are you doing? Good? So we're going to practice then, so there's no homework tonight. And then we will practice tomorrow